Okay. Does that go? Zoom out a bit more. There we go.
Alrighty, so today we're going to just work on 7G.1. That's what I'm going to go through. And I said it's going to take a fair while to get through. You can see there's 3 examples. They're very comprehensive, so let's just get straight into it. So we're introducing you to the binomial distribution. All right, and hopefully we've sort of done a little bit of it last year, some binomial calculations. But what the particular definition of it is that a binomial experiment is a repeated Bernoulli. So you might remember with the Bernoulli experiment, there's only one trial. A binomial experiment is one that you can repeat multiple times. Okay, you have n trials. But there's still only 2 outcomes, success or failure. And the experiment must be of independent trials. And all that is to say, I explain it very clearly below, but that is to say the probability must remain the same. Okay, if the probability changes, it's not binomial. Now we are going to refer to Pascal's triangle here in one of the later examples. So I'll talk about how to generate it and how it helps us with the binomial expansion alongside. And then we've got the binomial distribution function. So if we have some random variable, is there a Clash of Clans meeting? Some random variable, and then we're saying is binomially distributed. Okay, so later in the year you'll recap normal distribution, but at the moment we're referring to a random variable that's binomially distributed. It has a number of trials n and probability of success p. So that's a way that we can denote a binomial distribution using some simple notation. So I'm just reading through the page here. This means the variable x, yep. And then we have, for a binomial distribution, the probability of getting k successes is this binomial distribution formula. We'll make some connections. Okay, let's get straight into it. An unfair coin. Oh, that's not fair. It has a probability of landing on heads of 0.53. Use the binomial formula to calculate. All right, so I'm going to write out the binomial formula. Probability of x being equal to k is cnk p to the power of k, q to the power of n take k. Now I'm going to describe what each of these things mean. So we have the probability that the random variable has k successes. K is the number of successes. All right. N is the number of trials. P is probability of success. And Q is probability of failure. All right, and that's all the information we need, and we can substitute that in. So we've got an unfair coin. The probability of it landing on heads is 0.53. Part A, calculate the probability of exactly 2 heads out of 3. So this is the probability that the random variable is equal to 2 successes out of 3. All right, and so we're just going to plug in all that information. We have C, there are 3 trials and 2 successes. All right, we have multiplied by the probability of success to the number of successes, multiplied by the probability of failure to the number of failures. Now, Q, the probability of a failure is just 1 take away the probability of a success, yeah? They both have to add up to 1. So, do you guys remember this from last year? Seen this formula? Yeah, excellent, cool. So I'll just talk about what each component of it means. This here just means it can happen a number of ways, okay? If we're doing 3 trials and we get 2 successes, we could get success, success, failure. We could get success, failure, success. Or we could get failure, success, success. So there are 3 ways that it can occur. And so what this is saying is, how many ways can we have 2 successes from 3 trials? Well, there are 3 ways. Now we do that in our calculator. You don't need to sort of write them all out every single time, but you just need to be aware it's happening multiple ways, and this is the conditional probability of that event. So how do we bring that up in our calculator? what we get option. Alright, option. So you're in run map, you're in your main screen. Run map, we go option, we press the across arrow, we press prob, and then we've got NCR. Okay, NCR, and we put it in that order. So the way you would write this in your calculator is 3C2 times 0.53 squared times 0.47. That's what we're going to evaluate for the first one. I've got 0.3960, 0.396. Okay. Everyone all right with that? All right, part B. Find the probability of 6 heads out of 10 trials. 6 heads out of 10 trials. So this is when x is equal to 6 and the number of trials is 10. So let's just put all of that information in. We're going to have 10C6 times 0.53 to the power of 6 times 0.47 to the power of 4. Evaluating that one. I've got 0.227. Why? Let's maintain my good habit of writing and rounding. So if there's 10 flips, then the probability of getting 6 heads is 0.227. So that's B. All right, part C. The probability of 1 tail out of 4 trials. I might do that one here. 1 tail out of 4 trials. So that means 1 failure. All right. So I'm going to show you 2 ways that this can occur. If we have 1 failure, it means we have 3 successes. Right? It's the probability of getting 3 heads, and so that is 4C3. And then we have 0.53 to the power of 3, 0.47 to the power of 1. I've got 0.2798, 0.280. All right, so with this one, now I said the probability of a tail, 1 tail, and I defined a tail as a failure, but really that's arbitrary. It doesn't really matter what you define as a success or a failure, because if we want to find 1 tail, we could define a tail as a success, and we would perform this calculation, all right? It would be, we've got 4 trials with 1 success. Okay, we're defining getting tails as a success. That's times 0.47 to the power of the number of successes, multiplied by 0.53 to the power of the number of failures. And you can see, these are almost the same calculation, right? These parts are the same. All right, they're just written in a different order. And what you'll notice is if you evaluate this and this, they evaluate to the same number. Okay, so of course this calculation is going to be the same because it describes the same event. It describes the case when there's 1 tail. All right, we've defined a head as a success. If we've got 1 tail, that means we've got 3 heads. All right, here we define a tail as a success. We've got 1 tail, so it's the probability that the random variable takes on the number 1. Okay, part D says, what about the probability of getting the outcome heads, heads, tails, heads? Now this is a specific outcome, and so this is a conditional probability calculation. So the probability of getting the first heads is 0.53. The probability of getting the second head is 0.53. Then we're going to get a tails, and then we're going to get another head. So we're just calculating that. 7. Okay, so that's the calculation of that event, all right? And this has a specific order. It says, why is this different from C? This describes the event where there's one tail. There's only one tail. And so does this here. But they have different probabilities. Why is there a difference between these two calculations? And the answer is, this one depends on the order. This one has a very specific order where you've got heads, heads, tails, and then heads. Whereas this one, you get one tail, it could happen in any way. You could get tails and then 3 heads. You could get a head and then a tails and then another 2 heads. So there's lots of ways this can occur. In fact, there's 4 ways it can occur. What is 4 times 0.07? 0.28. Okay, there are 4 ways that this event can occur. Here is one specific part. So why is this different from C? This is a specific order of events. All right, whereas in part C, the calculation is unordered. It doesn't matter what order the events occur. Very good. All right, rub that out, let's move on. So that's introducing into the binomial distribution formula. Now let's see how it links up to Pascal's triangle. So, question, actually not yet, not in this question. All right, we've got a lucky dip contains 6 chocolate bars and 4 veggie delights. Okay, Wendy draws from the box 3 times without replacement. Is this a binomial distribution? Let's see, there's 2 outcomes, so there's a success or failure. Like Vinny and Lenny, you're shaking your heads, how come?
Because it's not the same chance each time.
Very good. Probability changes. When you remove something from the pool of all possible events, the probability of the next event changes, right? So our answer to part A is no, because the probability does not remain the same. The probability changes. Very good. All right, on to part B. Draw a tree diagram to illustrate the possible outcomes. All right, so I'm going to smash this out real quick. You can get a veggie bar or a chocolate bar. No, I'm going to do it like this. Veggie, chocolate, and the probability of getting a veggie bar, there's 4 out of 10, and a chocolate 6 out of 10. All right, then you can get a veggie and a chocolate. Veggie and chocolate. One veggie, one chocolate. A bit annoying because of the 3 branches, but we got there. Okay, and then we're just going to use this to calculate the events that it asks for. So it asks for, what's the probability of getting all chocolate bars? Okay, so we're getting all chocolate bars. We're taking, I'll get an alternative colour. this direction. Alright, we have to get a chocolate bar and then a chocolate bar and then a chocolate bar. So for part A, the probability of getting all chocolate bars, chocolate, 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 6 on 10 times 5 on 9 times 4 on 8. So we got 30, 120 on 720. You can simplify that, but I'll just leave it. Alright, all veggie delights. Gee, they sound good. So if we're getting all veggie delights, we're getting veggie, veggie, veggie. So that's going to be 4 on 10 times 3 on 9 times 2 on 8. So we got 8, 16 on 720. Okay. And then in the next circumstance, we've got 2 chocolate bars and 1 veggie delight. 2 chocolate bars and 1 veggie delight. So there's a number of ways that this can occur. Alright, we could get, I'm going to write them all out. We could get chocolate, chocolate, veggie, chocolate, veggie, chocolate, veggie, chocolate, chocolate. Alright, so we go to chocolate, chocolate, veggie, that's this part. Alright, so that's 6 on 10 times 5 on 9 times 4 on 8. If we got chocolate, veggie, chocolate, we've got 6 on 10 times 4 on 9 times 5 on 8. And then for the last one, veggie, chocolate, chocolate, 4 on 10 times 6 on 9 times 5 on 8. Okay. Now, all of these look like they're different calculations, but they're actually all the same. When you multiply fractions, right, it's just the top times the top and the bottom times the bottom. And if you notice, all of the denominators are 10 times 9 times 8, so all of the denominators are 720. And all of the numerators have the number 654, albeit in different orders. Alright, so 6 times 5, what, 30, 120. So the probability of the first event is 120 on 720. The probability of the second event, 120 on 720. And the probability of the third event, 120 on 720. So 360 on 720, that's half. Alright, so the answer for part C or part 3. You basically got a 50% chance of getting 2 chocolates and 1 veggie. Okay. Alright, let's move on from there. Let's get on to number 3. We've got Pascal's triangle. So we've got the same problem as in the problem above. Now consider a lucky dip operator who replaces whatever is drawn. Okay, so now that we've got replacement, it satisfies the binomial properties. It is now a binomial distribution. Part A, describe why this is now binomial. Two outcomes, success or failure, and probability remains the same. So if it satisfies those properties, binomial distribution. Part B, use Pascal's triangle to expand P plus Q to the power of 6. So let's flip back to Pascal's triangle here. And I'm just going to draw up on the board the 4th row and the 5th row, right? And I'll show you how to generate the 6th row. So we've got 1, 4, 6, 4, 1. And then we've got 1, 5, 10, 10, 5, 1. Alright, so the way it's generated is that we have 1s going down all of the diagonals, right? The 1s are going on the diagonals. Now 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and the 1s on each end. So that means for the next row, we're going to have a 1 on each end. And then we go, okay, 1 plus 5, 6, 5 plus 10, 15, 10 plus 10, 20, 10 plus 5, 15, 5 plus 1, 6. Alright, everyone okay with that? Okay, now we're going to use that And so hopefully you can see the relationship there between those numbers and the expansion. So if we have P plus Q to the power of 6, all right, this is what it tells me. It's going to be one lot of P to the power of 6, Q to the power of 0. All right, and then we're going to have plus 6 lots of P to the power of 5, Q to the power of 1. All right, I'm going to write the next one and then I'll provide an explanation. Plus 15 lots of P to the power of 4, Q to the power of 2. Okay, hopefully you can see what's happening. The power of P is decreasing. It starts at 6 because we had P plus Q to the power of 6. It starts at 6 and it's going down by 1 to the power of 5, to the power of 4. Q starts at 0 and it goes up by 1. All right, we'll keep going. All right, and we don't need to express the Q to the 0. The only reason I do that is to demonstrate the pattern, right? Q starts at 0, goes up by 1, 2, 3, 4, 5, 6, and same with P, starts at 6, goes down. But any number to the power of 0 is 1. All right, so what we have here is 1 times P to the 6 times 1. So we can just get, like, I only put it up there just for the sake of making the argument. At the end here, we've got 1 lot of Q to the power of 6. Okay. So, let's look at the question. Use Pascal's triangle to expand. Excellent. A success is when Wendy gets a chocolate bar. There are 6 trials. Use your expansion to find the probability of Wendy getting all 6 chocolate bars. Okay. So we're going to define P as the probability of a success. Now, there are 6 chocolate bars and 4 veggie delights, which means our P, the probability of success, is 6 out of 10, right? So, if we're looking here, what's the event that corresponds with 6 successes? It's this one here. Steve, remember that number out the front? There's only one way it can occur, and it's if you get a chocolate bar, and then a chocolate bar, and then another one, and another, until you've got 6 chocolate bars all in a row. There's only one way that can happen, right? And so, so let's answer the question for part C, part 1. Okay, we want to know what's the probability of 6 successes. Well, it's 1 times 6 on 10 to the power of 6. $729 on 15,625. Okay, on to part 2. What about 4 chocolate bars? Okay, so 4 chocolate bars means 4 successes, and it corresponds with this event here. Okay, 4 chocolate bars, that's when we have P to the power of 4, the number of successes, right? So we have 15 multiplied by P to the power of 4, multiplied by the probability of a failure, 4 on 10 to the power of 2. Point 0.6 to the power of 4, 0.2 to the power of 2, 0.07776. Okay, so look, here's the connection I want to make. All right? This is the same as this. Six trials, 4 successes. Sorry, that I've messed up the example. That should be, we want 4 out of 6, and we want 4 out of 2. Alright, so, I mean, back here as well, that should, no, that's correct, no, that's correct. Probability stays as 6 on 10, yeah, no, that's correct. 4 on 10. But there are 6 trials. Yeah, no, that's all fine. Okay, so here's the connection I want us to make, right? C64 is this number 15. The possible ways of getting the number of successes is given to us from Pascal's triangle. Okay, so I just want to make a connection there. That's why we're doing this one. And then last one, exactly 2 veggie bars. 2 veggie bars means 2 failures. All right. And 2 failures means 4 successes. And so the answer to part 3 is the same as this one, 0.0778, because that's the event that corresponds with 4 chocolate bars, 2 veggie bars. Okay, how many possible ways are there of getting 5 chocolate bars out of 6 trials? 5 successes out of 6 trials, that corresponds with this event. How many possible ways are there of it occurring? 6. That's what that number means. So to answer part D, 6. 6 possible ways it can occur. All right, and it's also equal to C65. If you put that in your calculator, you'll see that it evaluates to 6. All right, now it does say to list them, so that's like when you get chocolate, 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 veggie, chocolate, 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 veggie, chocolate, 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 veggie, chocolate, chocolate, and just keep going through until the veggie's been in each respective position. All right, there's lots of ways it can occur, right? Okay, part E, calculate this event and interpret its meaning. Let's jump up here. Got to finish before recess. C, 0.6 to the power of 3, 0.4 to the power of 3. All right, so we can calculate that. All right, what's this? Number of trials, number of successes, probability of success to number of successes. So we can already anticipate what it is. This is when there's 3 successes and 3 failures. All right, so let's calculate that quickly. Got 0.2764. This is the probability of getting 3 chocolate bars and 3 veg in any order, right? Doesn't matter what order it happens in. There's 20 ways that can occur. Try right limit. Okay, part F, what is the probability of getting 3 chocolate bars in a row followed by 3 veggie delights? All right, so that means chocolate, 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 veggie, veggie, veggie. So that's 6 on 10 times 6 on 10 times 6 on 10. That's 6 on 10 to the power of 3 multiplied by veggie delight, 4 on 10 times 4 on 10 times 4 on 10, 4 on 10 to the power of 3. Let's calculate those. I'm going to write out all the figures here, just to make the case, all right? Because here, so we're going to keep reiterating it, it's a thing that pops up in your test. Here, we said, what's the probability of getting 3 successes, right? 3 chocolate bars in any order. And if you evaluate this, you'll see there's 20 ways it can happen. We get that from here. There's 20 ways of getting 3 successes and 3 failures, all right? This is one of those specific ways. This relies on the order of this event occurring, which is why the probability is heaps lower. Even though it corresponds with the same number of successes, it depends on the order in which they're drawn out. And I said there's 20 ways it can happen. If you multiply that by 20, this is the number you get. Okay? And even then, like, you can see the relationship between this calculation and this one. All right, especially when it's written out like that. Here, 6 on 10, 0.6 to the power of 3, 0.4 to the power of 3. It's missing this component of it. It's missing this 20 out the front because it's only one specific way of it will prepare. Very good. All right, told you it'd be a long one, but hopefully that's pretty comprehensive.